Hello, everyone, and welcome to this year's edition, 2021, of QLSC 612's Introduction to Data Visualization in Python. My name is Jacob Sanz-Robinson, and I will be your instructor for this. However, the presentation's original contents were written by Jacob Vogel and Pia Hellholtz. Now, you will be able to find Pierre, recognizable by his fantastic beard, in the containers module of this same course. So, the purpose of the data visualization module is to teach you the basics of data visualization in Python, and to help you use data visualization as a tool to better understand your data, as well as creating publication quality graphics. So it will guide you through the process of familiarizing yourself with data through visualization and choosing plots that display the information accurately and clearly. It will provide you with instructions and examples on how to use multiple widely used plotting libraries that exist in the Python ecosystem. And the way this is going to work is that we're going to go through the slides, and then we're going to move on to a Jupyter notebook, where we have a few code examples based on real data to illustrate how you do this. Then later on, we're going to have the live tutorial session with, I'm looking forward to the live debugging on that. And in that tutorial session, we will have more exercises using a few of the different libraries that we didn't cover in this lecture. So without further ado, let's get started. So, first up, Python offers a wide array of options that you can use to visualize your data and create figures. There are lots of different things which set these different libraries or APIs apart, and they have different strengths and weaknesses. One of the main key ways in which these packages can be different from one another is that some of them are low level and some are more high level. Low level just means that you probably have to create the figure from the ground up, specifying all the details, and that has the strong point that you can specify all the details. So whenever you are tweaking to your heart's desire to make that perfect figure for your paper, you will be able to do it in a low-level API. High-level APIs, on the other hand, make it quite easy and quite quick to get a very pretty plot straight out of the can, but they often lack the features to manipulate the figure at a low level and tweak it to your heart's desire. Another way which these APIs commonly differ is in their output format. Some of them output static images, which is very useful if you just need an image to include in your paper, for example. Some of them have HTML output, which is very useful if you want to embed your image in a website. Some of them offer interactive plots, so once you've created the plot, you can play with the plot, maybe swivel it around, maybe zoom in, maybe click on a couple of different things to change what you see. And they can be useful for showing off your data, say in a presentation, or for just exploring your data, seeing it nicely and clearly. Some of them are very domain general, meaning you can just create your average graphs, your average charts, like what you see in most papers. And some of them are very domain specific. So an example that comes to mind are the neuroimaging APIs, which you can use to plot brain imaging data very, very quickly and easily. So amongst all of these different modules, there are a few which stand out and are perhaps more famous or prominent or versatile. One of them is matplotlib, which is a fairly low-level one, and it is based on the MATLAB image plotting system, which I'm sure many of you have worked with. Based on matplotlib, but slightly higher level and thus slightly nicer looking, is Seaborn and Pandas, and then there are interactive plotting tools too, such as Bokeh and Plotly. So you might be thinking, well, that's cool, I'll just get a really high level one, which will give me beautiful plots, and it will probably suffice for my needs, and that's it. No need to learn the low level one. But this isn't quite the right way to see it. And it's good to know some of the principles of some of the lower level ones, like matplotlib. For example, often, if you want to have an article ready quality figure, then you will need or want to tweak it in some ways. And sometimes doing so in Seaborn is problematic, or you just can't. And often, because Seaborn is based on Matplotlib, you will be able to go down one level in your packages and do that tweaking in Matplotlib. So, in this lecture, after we've gone through the slides, we're going to go through a Jupyter Notebook, which shows some of this stuff in practice. And if you haven't already seen the course material repo, here is the link to it. And the name of the file that we'll go through is Python visualization for data.ipynb. But this name might have changed. There should only be 3 files in the repository for this module, so just go through those and I'm sure you'll find the right one. So, graphics are pretty cool, and if you use the APIs that I'll show you in this module, they can also be pretty fancy. But being fancy and cool isn't enough. Graphics should also be honest. And here is a screenshot from a news broadcast. And we can see here that they omit the scale on the y-axis, and it doesn't start from 0. And therefore, it makes the difference between the 2 columns look very large, when in truth, if we plotted them with scale correctly, as you should, you could see that the difference doesn't look quite as impressive. And similarly for this figure on the right, where one of the columns is 35% and the other one is 39.6%, but the difference looks a whole lot bigger. And all of this to say that it can be easy to misguide people with your graphics, and it can be easy to, say, emphasize a certain story or fuel a certain narrative by tweaking your graphics enough. And unless people really know what they're looking for and how they might get caught out, it can be very easy to misguide them. So as I think it was some Spider-Man thing or something, with great power comes great responsibility, and you should be responsible and honest and use your graphics to display your information as accurately and clearly and transparently as possible. Creating visualizations of your data isn't just about creating a pretty figure for publication. Data visualization can actually be an extremely potent tool to understand your data properly. So what does it mean to understand your data properly? Well, one of the things that it means is to learn the structure of your data and what it looks like properly. And you can use data visualizations to see the distribution of your data. You can also use it to identify summary statistics, identify data that is missing, identify the structure of your data and what dimensionality it takes, and also to test and explore associations in between variables that are in your data. However, one thing you shouldn't do when going on an exploratory analysis of your data through visualization is going on a fishing expedition. And basically by this we mean that you should just not be searching your data for significant associations, right? You shouldn't just be testing every single association until you find one that works and then present the one that works. You should also not be using data visualizations to hide certain things or perhaps emphasize certain things that might not go with your story. So as soon as you have seen your data and visualized it slightly, you might actually find that you are already biased in the hypotheses you are making, which, as we will see, can be a risky thing. So when we speak about data analysis by design, what we mean is that depending on the type of problem you are solving or on your approach to this problem, there might be different steps to take. For example, if you have a hypothesis, it can lead to a certain approach and certain steps within this approach. Typically, if you have a hypothesis, what you're going to do is you're gonna first collect data for it, then perhaps do a plan for how you're gonna analyze your data, then do pre-registration on this data. And meanwhile, if you don't have a hypothesis, you're probably doing more of an exploratory analysis. And then when perhaps you found something, then you'll want to do cross-validation or a left-out test set or or test your findings on an external data set and see how they generalize. and such as all these things that you might have heard of from the machine learning world and how they evaluate their models. Not differentiating well in between the two approaches I described on the last slide can lead to what we know as the train of stubborn null hypotheses. And this basically means that, say you start designing your study, you start collecting data for it, then you test your null hypothesis, maybe things worked out as you wanted to, maybe they didn't, and then if they didn't, you plan an alternative hypothesis. And then at this point, what you're doing is that you are going to your data and then searching for this other hypothesis, and now you're in data exploration mode. So you're doing data exploration now, you're not doing confirmatory research anymore. And then you take this arrow and you're back at the beginning and you're stuck on this cycle. However, there's nothing particularly wrong with this, but there is a problem that arises when people are not transparent when they switch between confirmatory and exploratory research. So all of this to say that you should be honest in the story that you tell. And there are some considerations that are worth having when it comes to data exploration. For example, if you have smaller sample sizes, maybe your results are more biased and less generalizable. It is also worth considering that you should maybe publish your null results. They are also important. They are something that has been found. You should make them known to the world. You should definitely validate everything you find and validate it in any way possible, maybe against external data sets, maybe with other people. And you should always communicate and get people involved, perhaps through posters and collegiate communications, and ask for their opinions on this sort of stuff. And it helps out at the end of the day. So, in a throwback to your favorite undergraduate statistics class, here are a few data distributions with a few labels which could fit these data distributions. And for example, this first one looks normalish. It somewhat resembles that normal distribution that we all want to see, I guess, and that would make our lives easier. Here is something that looks like a skewed distribution. Here is something that looks like ostensibly a bimodal distribution, probably a bimodal one. Maybe not though, but that's kind of what it looks like. And then here is something that looks like a floor/ceiling distribution, and something that looks almost like a Laplace distribution. And it's worth mentioning that in real life, the answers are rarely clear-cut. You usually don't just see a distribution and go, oh, it's exactly this one thing. And getting a normal-ish distribution or a normal distribution is practically like winning the lottery and very rare in practice. Different data distributions have different ways to tackle them. And oftentimes in real data distributions, the distributions, as I mentioned, are not pretty, or the assumptions to have a particular distribution don't hold, and therefore tackling them in a conventional manner it can be challenging. Parametric tests, such as t-tests and ANOVAs, require assumptions that are satisfied. For example, we require that the data follows a normal distribution and that there is a homogeneous population variance and things like that. But say, what happens if this doesn't hold? Well, non-parametric tests are one strategy, and they're basically a method of statistical analysis that does not require distribution to meet the required assumptions to be analyzed. So they can be a feasible alternative when the data is skewed or the population size is too small to validate the distribution. Categorization or encoding is another possible strategy and method, which means that you divide up your data by giving it new labels according to newly re-specified categories. And perhaps now you can do something with your data now that it's been recategorized. Another possible approach is normalization, and normalization consists of the creation of shifted and scaled versions of the statistics, where the intention is that these normalized values allow the comparison of the normalized values with more ease. However, following these strategies requires that you keep different considerations in mind. And a few of these are the degrees of freedom, which is basically the number of independent ways by which the system can move without violating any constraint which is imposed on it. The interpretability, which relates to how clear and how readable your approach is and your strategy is, and how if you showed it to someone, they would be able to understand it and wouldn't just think you're insane or not understand it at all. And then you also have to worry about the generalizability, so how well it could apply to different pieces of data which might be similar. What are some ways of visualizing your data? And we are going to start with univariate data. And this is basically data that consists of observations on only a single characteristic or attribute. For example, imagine a Python list that contains the ages of all of the people in this class. And then we just wanted to visualize all of those ages. That would be a univariate statistic. And say your data is categorical and it belongs to two categories or just many categories in general. Well, in this case, a good option is a count plot. And an option which is a bad option and is very much not recommended is a pie chart. And this is due to the fact that pie charts, they've ruffled some feathers in academia recently because they take up more space and are harder to read than alternatives. It turns out that the human brain is not very good at comparing the size of angles, and because there's no notion of a scale in these, then reading accurate values of them can be somewhat difficult. If your data is scalar, then there are a few different ways you can do this. For example, these four plots here, such as a histogram, a KDE plot, a strip plot, or a ranked strip. And then here we can see all of the Seaborn commands, so the Seaborn API, how you would plot them. So assuming that you have your univariate data in a list, say the list X, then it would be as simple as calling Seaborn dot distribution plot dot dist plot and then calling that function on your list. And here we have that for each of these four plots. So what if you want to visualize bivariate data and you want to have, say, determine the relationship between two variables? So firstly, note how Seaborn requires you to have two lists as parameters to the functions you call as opposed to one list like in the previous slide. And if you have two categorical variables and you want to plot them against each other, then perhaps a scatter plot is a good sort of way to do this. And there's a few ways to do scatter plot-ish looking things in Seaborn. One of these is the reg plot or the regression plot, which is used to plot the data and a linear regression model fit to it. Then there's the image plot, which is a 2D scatter plot with an optional overlaid regression line on it. And then finally there's a joint plot, which displays the relationship between the two variables as well as 1D profiles, so univariate profiles in the margins. If you want to plot categorical versus scalar, perhaps one good way of doing this is a density plot. And you can see here that this can be done with the joint plot option. And if you want to have two scalars, so you want to plot scalar versus scalar, then a hex plot could be a good option for this. However, we will see later that these work much better for large sample sizes. And when you have too small sample sizes, it just looks like some clumpy hexagons, and it's not quite that useful. Continuing with our quest to visualize bivariate data, you might be thinking that if you have two categorical variables, you can perhaps use a bar plot or a point plot to plot these, and in truth that's probably not a great idea. Bar plots in particular, it's very easy to misrepresent data, as we saw at the beginning. They boil down the data points to a single mean and often fail to convey the nuances of the numbers. For example, very different datasets can be described by the same bar graph, theoretically. And if you want to plot categorical versus scalar variables, then some good options are the box plot and the boxen plot, which also give us some information about the quartiles and the distributions. And if you want to plot scalar versus scalar, similarly, violin plots are very useful, and strip plots, as you can see here, also have a role to play. One of the newest sort of plots which I've seen around is the rain cloud plot, and they really offer the best of a lot of the different worlds. You can see the data points in the scatter plot. They include a box plot which allows you and the distribution, so you have all of the information about the distribution, and they're just a very informative way of packing a lot of data to see what your data is really saying in a little image, in a little graphic. So when it comes to visualizing your multivariate data, you might want to visualize several pairwise relationships once in your variables. So there are quite a few ways to do this, and one of them, for example, is a pair plot, as you can see here. Another one is a heat map, as you can see here. And then finally, another option is a cluster map, which uses the information in the data to create clusters or categories in it. Furthermore, you can also visualize the interaction between three variables at a time with 3D plots, such as the 3D surface plot or UMAP dimensionality reduction plus 3D scattering. So now that you have been equipped with a basic approach and philosophy towards, say, confirmatory and exploratory data visualization, and you have a list of a possible bunch of Seaborn functions and plots that you can use in common situations, it's important to fit in a word on style. Now, when I refer to style, it's not just about making your plots fancy, though by all means get creative and frisky with it and have some fun with your plots. It also factors into the accuracy and the transparency of the plots. For example, some color maps, such as these vendor color maps, have ranges where features disappear based on the low sense of contrast between the colors. And it can also happen that false features that are not in the data are just introduced into the data, seemingly, by these colors. And just as was the case with the news bar graphs at the beginning of this presentation, they can also sometimes make differences between certain data points seem much bigger than they actually are. So you have to be careful when you're using a color map, and we recommend always using perceptually uniform color maps to circumvent this problem. You can Google them, there's quite a few of them, and we recommend you use these for the purposes of creating your scientific figures. Another point on style that is important to consider is that people can have color blindness, and some color maps don't cater to this demographic. However, there are plenty of color maps that work both in grayscale and in color without losing information throughout. And these can be especially useful when the publishers want to charge you for including color images in your publication. So, on that note, to elaborate a bit on this figure, we can see that in A there is a perceptually uniform grayscale color map. On B there is the jet color map. On C there is the jet color map as it would appear to someone with a red-green color blindness. And on D, there is the Viridis color map, which is the current gold standard in many plotting packages. Now, below each image, there is a corresponding color map perceptual sensitivity plot, which compares the perceptual differences of the color map to actual underlying data differences. And they mention that an example of how the data can be misinterpreted can be seen in the yellow spots in B and in C, which appear to represent significantly higher values than the surrounding regions. Then, in fact, when we see the dark red parts in B and the dark yellow parts in C, they actually represent the highest values. But for someone who is red-green colorblind, this is made even more difficult to interpret due to the bright band in the center of the color map. And those values can be difficult to distinguish. Another thing worth mentioning is that as you find yourself mastering these APIs that I will speak about shortly and have spoken a bit about, you will find that you save a lot of time by using Python for all aspects of plot creation. You will see everything is customizable and can usually be done efficiently, and you'll find yourself wondering how you ever got a figure done in Excel, for example. Another point that is important to speak about is that you always want your figures to be completely reproducible. And this means that you will always want to have all of the code and all of the data you used with the code to generate the figures available if you find yourself in the position where you need to reproduce your results and your graph. And you should also consider hosting them on a place like the Open Science Framework or on GitHub, which are specially meant for this sort of thing and can make reproducibility a lot simpler and less of a headache. And it genuinely is an important thing to keep in mind. There's also many resources which will be helpful to continue mastering data visualization. There's only so much I can cover in an hour, and while I hope I leave you with a good foundation on this, there are places like this website, the Python Graph Gallery, which is very cool. It has a ton of graphs in it, and whatever your plotting purpose is, there's a good chance that the graph you need is here, or at least something very similar you can take inspiration from. I'm just going to click on the ridgeline one here because they look cool, and you can see that they summarize basically they summarize what the graphs are about, and they usually have Python code that you can click and then see exactly how the graphs are generated. So that is extremely useful. And then there's also a similar resource for the color maps in Matplotlib's website, and they have a bunch of information about different color maps, and you can read about them and different types of color maps and different names of color maps, and choose which ones you want to use and how to modify them and make your own color maps, and it's all there on the website in a very nice way. Lastly, remember not to use the jet color maps. As I showed you in the past figure, they can have some issues, and there's some outrage against them. And that's pretty much it as far as the slides go. So soon we'll get cracking on a Jupyter Notebook, with some actual examples. But before that, then, what are the big conclusions that I want you to get out of this slideshow? Well, firstly is that visualization is a useful tool to figure out what is going on in your data, as well as to make very nice figures for your papers. Another important thing is that all your figures should be reproducible, and you should make your code and the data that you use to make the figures accessible if you can. You want to display your data without forcing a particular perception of it. You always want to be accurate in what you display, really, and you want to be completely transparent. You don't want to just be fueling a narrative. You want to find the optimal way of being very clear about what you're doing. You also want to be careful that the trends you see in your exploratory analyses don't bias your subsequent hypotheses and the tests that you then perform. And then finally, you should remember that while the high-level libraries are very awesome for getting things done quickly and tend to look fantastic straight out of the can, it is very useful to know the low-level libraries, and you will find that being able to tweak these very low-level features is a huge asset when it comes to making the perfect figure. So now let's get on with the notebook. Welcome to the second part of this lecture, whereby we will be doing visualization of different data types in Python. And what we're going to do is we're going to just visualize some actual data, and we're going to focus on using one of the libraries I spoke about during the slides, which is Seaborn. And Seaborn is pretty high level based on top of matplotlib, and it's designed to make nice looking plots quickly and in an intuitive fashion. So we're going to get a bit of a flavor for that right now. First thing we're going to do is import all of the libraries we're going to need. So the OS library, pandas to deal with data frames and, just the data in general and reading it out. NumPy, however you say it. I think it's probably NumPy, right? That makes sense. To do all the numerical calculations, matplotlib, and Seaborn, which will be our protagonist. So go ahead and give that cell a run. Next, we're gonna need our data. So there's this OpenNeuro dataset, and if you click it and open it, then you will see that you can download participants.tsv here. So go ahead and do that, and when you've got your download, you are going to want to change this line in your code so that it points to the directory and the file, wherever that may be on your computer. Then we're going to use pandas to read in this data frame, and then we're going to see what's inside it. So we're going to run that frame, and you can see that it's loaded up our dataset successfully. And then what are our different variables? So we're going to use the columns feature, pandas, and we can see that there's a whole bunch of different variables that we can use, which indeed are the columns of this TSV file. The next thing we're going to do is some univariate visualization based on one of these variables. So let's say we're going to choose the age variable. So we can print some summary statistics using the describe function from pandas. And you see it, and it gives you, lots of stuff you need. The mean, the min, the max, the interquartile ranges, all of that sort of stuff. Now say you wanted to find the distribution of your data. And a simple way to do this could be to try and use a histogram. And with Seaborn, which we imported as SNS, you literally just need to call the distplot function with a single argument, just the column of the data frame that contains the univariate data you want to display, and that's it. And then you just run this cell, and boom, you have a rather nice looking distribution. And then there's a whole bunch of other arguments you can provide optionally, which change the way stuff is. So for example, we can uncomment this line and change the color to something slightly different. We can change the color of this to be black. We can also say take off the squiggly distribution line from it by uncommenting that line. You can just play around with that. And there's other options you can play around with too, should you read more about it. So that looks kind of like the floor and ceiling distribution from the slides. But, we might want to find more stuff about it. We might want to try different approaches to see how we transform our data. And one easy way to demonstrate that would be log normalization, and it can be done very easily with NumPy. So we simply import NumPy, which I've already done above, but we make sure we do it here, and then we calculate the log of everything in that column, and then we once again just plot our histogram in much the same way as above, but now we do it of the column which has been transformed by NumPy with the log command. And if we do that, we will find that it displays this, and that's cool. We can see a bit more about it. And there is, of course, another approach that you can use to do these log transformations, and it might be better practice as it's quite easy to undo, and it's something that generalizes to pretty much any transformation you might want to do to your data. And you can do it with sklearn, with the sklearn library there, and you can use their function transformer to do it. And as I said, this has the advantage that you can easily reverse it, and it's perfect for basing a transformation of one data set and then applying it to a different data set, so it makes it very easy to test in a generalizable way. It has some disadvantages. It always expects 2D data, and it's slightly more code, but as you can see, it's not that much either.
So pretty much you just call the function transformer with the numpy function of the logarithms as an argument, and then you simply reshape your data such that it is in 2D now, so it has 2 dimensions, and then we can fit the data, right? We can fit this 2D data using the fit function, and then we can finally do the transformation. So we've done all of that, and then we might want to say compare whether the 2 columns which we performed the log transforming on are equal, the one that we did with numpy or the one that we did with sklearn and its function transformer. So if we run that, we will see that it gives true, the equality comparing these 2. And of course here we've just chosen, since it's in 2D, we just had to choose one of the columns to do it. We can see that it's true. And then we can easily reverse the transformation with the sklearn one to recuperate the original values for the age that haven't been log transformed. So we do that, and then the inverse transform should be the same as what we had as our original values. We can test that, and it is once again true. One of the other strategies that I mentioned during the slides is that of categorization. So there are 2 types of categorization that have already been done for us in this data set. And we can visualize this with pandas or with Seaborn. Pandas has the value counts function, Seaborn has the count plot function. So using pandas, if we did it, right, we could see what happens. It gives us all of these different categories and how many people are in them inside that data set. Similarly, we can do we can use the count plot option. And we can see that it also gives us a plot which shows us how many children and adults there are in this data set. Next part of the notebook is to do with bivariate visualization. So in this case, linear versus linear bivariate visualization. And we might want to see the association between 2 variables. So for example, let's say we want age and a cognitive phenotype like theory of mind, or which is a measure for intelligence, so to say. And we can start with a scatter plot, and we can extremely easily with Seaborn use the regplot function to build a scatter plot. So here the important thing to note is you have to pass 2 variables now as arguments, as opposed to 1 variable with the univariate visualization. So you can see here that as our x we have passed age, and as our y we have passed our theory of mind measure. And as you see, this gives us a nice scatter plot with a regression line going through it. And it's important to note that regplot will automatically drop missing values. It will drop the whole pair of them. And there's also quite a number of nice arguments you can provide to it to change how your plot looks slightly. So once again, we've included a few of them here. But say, for example, you just wanted the scatter plot, you didn't want the regression, well, you just take off, right, you just make the fit regression line false. And then you have the same thing, but without the regression line. So you guys feel free to play around with all of those. And yeah, so now's a good time, I guess, as any to mention that Seaborn is built on top of matplotlib, and any object which you could build in Seaborn, you can also build in matplotlib completely from scratch. So in this case, the regplot function in Seaborn is built on top of the scatter function in matplotlib. So if we use matplotlib, which we imported as plt plot, and we call the scatter function, and we provide, once again, the x and the y variables, same as above, then we plot them, and we see that we do have a nice scatter plot. If you wanted to get a little more sophisticated in your visualizations, you might want to plot a couple of different ones and use the joint plot function. And then you can change the kind argument to change the sort of plots that you see in it. So, yeah, basically we can see here that we have a few different kinds of plots. We want to have a scatter plot, a KDE plot, and the hex plot, as we saw in the lecture earlier. And then we're just going to call the Seaborn joint plot option, and we're going to provide our x variable as age, the y variable as the theory of mind, and then the kind argument. And we're just looping over these different kind arguments and plotting with them. And then we're showing the plot. So you do that and you can see that indeed 3 different visualizations are produced. And the first one is a nice scatter plot, and the second one is the KDE plot, and then the third one is the hex plot, which would probably work better if you had a larger sample size. So each of these graphs might have a different ways and different moments when they seem clearer on different kinds of data. So you can change the types, the kinds, quite a lot. And you can see which ones display your data with most clarity. And here it just says that this would have probably looked a bit nicer if it was a large sample size, because hex plots work best that way. And if you have a scatter plot with tons of data, and then you have a hex plot with tons of data and sort of closely clustered and clumped together, the hex plot deals with the density in a much clearer way. So what we're doing here is we're just generating a bunch of random data, right? We're assigning a mean and a covariance, and we're creating just a random bunch of data here using NumPy. And then we are going to do a joint plot with a scatter plot and a hex plot. And we're plotting these as a joint plot with Seaborn. And we're going to run that. You can see that there's a ton of data points. And in the scatter plot, it's not always exactly that clear what's going on. You can kind of tell what's going on, but it's not as good as the hex plot, where we can use the colors also to tell us exactly what's going on density-wise and help us visualize the density in this way. However, it is worth noting that the joint plot is a different type of object, and therefore it follows slightly different rules when editing, right? So it's slightly different from just the scatter plot object. And that is one of the biggest drawbacks of Seaborn. Now, for example, if we wanted to create pretty much a very similar plot using both the reg plot and the joint plot functions, you can see that there's different ways of doing it. And this one uses a joint plot, and this one uses the reg plot, and they pretty much build the same thing, but there's different syntax to do so, right? So you can examine that syntax in a little more detail whenever you wish to go through the notebook. But all that to say that the main point is that when you are using a function from Seaborn, or from any library, but in this case for Seaborn, you will want to read the documentation of it. You're going to want to go online and see exactly what arguments you need to pass it and how to use it. Because if not, you might be in for some frustrating surprises. And usually these libraries do have a pretty good documentation built for them. And then finally, for this section, lmplot is another nice option, a sort of scatter plot for observing multivariate interactions. However, it can't simply take 2 arrays as input, but similar to R, for those of you who have used R, you have to pass it some data, and this data can be a data frame, for say from pandas, and you have to supply it also with variable names. And luckily for us, on our data, we already have our data in a pandas data frame, so this isn't too much of a headache. And we can examine the relationship between age and theory of mind, and how it varies according to gender. And we can do this using the hue, the column, or the row arguments too. So this is how we do that. We just call the lm plot with our x variable, age, our theory of mind variable as y, and the phenotypic kind of data frame as our data. And we have the hue, so separating by hue, by color, we separate the gender in that way. So we pass those arguments, and you can see And you can see that this isn't the nicest plot in history. It probably doesn't convey this data all that well or that clearly. It looks a little squashed up. And this sort of plot can be suboptimal at times, and the reg plot is generally more flexible. You can read about this type of plotting at this link to the Seaborn documentation, their tutorial on the different distributions. But we just thought it's good to mention it, and once in a while these LM plots can indeed come in handy. If you recall the slides, there were a bunch of ways of visualizing a linear versus a categorical sort of thing. And tons of ways to do this kind of bivariate visualization. So we're going to look at the same relationship as before, but now we're going to use the age group variable instead of age. And there are many ways to visualize one of these relationships. And really, each plot has its pros and cons. And at the end of the day, you should probably just try all of them and see which one suits the data best, which one looks the best, which one does its job the best. If you go through this slide, there's nothing too fancy. We're just feeding the x and the y variables and the data frame for everything that isn't an adult. We're just feeding it into pretty much just functions that make these plots. So I'm going to run it, and you can see that I've generated bar plots. I've generated a box plot where you can see the distribution, box end plot, a violin plot, strip plot, point plot, and you can see that they all show the data in slightly different ways. And as I was mentioning earlier on in the presentation, line plots and bar plots are typically not good news because they don't show the actual data as opposed to just a summary of it, and therefore they can mask stuff, and they're just not really that great. But let's say you have to use a bar plot for some reason. Maybe someone in your lab insists you do, or I don't know, for some reason you need to use a bar plot. Then one cool thing you can do in Seaborn is that you can overlay different types of plots on each other very easily. So then you can produce a bar plot that also has information with it that helps it be slightly less useless. And for example, if you run this, you can see that I'm generating really a bar plot here. Right, and then at the same time I'm also generating a strip plot, and therefore when I run this code, we can see now that it is in fact the bar plot, but with the strip plot overlaid on top of it. And this is much more useful to give us information about this data. And really the Seaborn documentation is very nice, so you can go and you can click on this link here and it will help you with it. And if you're ever having trouble deciding what sort of plot to use, then you can check out the rain cloud plot, which I mentioned also during the slides, and it combines a ton of plots in a very nice way to create a very thorough visualization of your data. And I don't think this is necessarily included in the things you sort of had to install for the course in the setup instructions, but there's a great library called Petite Prints which you can use to do it, and you can just go ahead and do a pip install Petite Prints in your command line to install this, or if you want to do it through conda, you can do conda install -c and then conda -forge and then Petite Prints. And or just Google the Petite Prints library and you'll find it there for sure. And basically this cell just shows how you would go ahead and generate this. And as you can see here, it gives us a very nice visualization of the data with this rainbow plot, and basically just includes a bunch of different plots within it. The last part of bivariate visualization is visualizing relationships between two categorical variables, so categorical versus categorical. And if we want to do this, since we're usually just going to be looking at quite the simple statistics such as counts or something or percentages, then sometimes a simple bar plot is fine. And in this case, we're looking at the age group versus the gender. And we have the pandas crosstab function, and this helps to sort the data in a way which is somewhat intuitive. So if we do that, we can see here that it has sorted the data nicely for us by age group and then gender. And then we can plot this directly inside Pandas, so we're not even using Seaborn for this. Pandas has some plotting functionality, and we're just using our index is the age group variable, and then the columns are given by the gender variable. And then we're just plotting a bar plot for that. You can see it gives us the count, the amount of people per gender per age group. And this plot gives us the absolute counts, but sometimes it's more useful to visualize differences in proportions across age groups. And to do so, we actually need to do this manually. So we have our crosstab function, and it does, it organizes the data as such. And then we have to apply something to it to make it a proportion, really. So we just have a lambda function here that's dividing everything by the sum of everything in the column. And if we run that, then we can see that we have the differences in proportions here. The last thing we're going to speak about in today's lecture is the style points then. And as I was mentioning in the lecture, you will be surprised, amazed, hopefully in a positive way, at how customizable your Python plots are. So you can change every little thing about them. And when you're first exploring the data, this might not seem like a big deal. But when you're actually communicating your data for manuscripts, posters, talks, or anything, you'll really appreciate being able to create very optimized plots to your own tastes and that convey the information exactly how you want to see it. And once you know the relationships you want to plot, spend some time, dish out some time adjusting all of the colors and the layouts and the finer details of your plot. And all of this with the goal of maximizing the interpretability and the transparency of what you are plotting. And if you have a little more time, then you might as well go ahead and make it a beautiful plot, because they're nice to look at. And you can easily edit everything using the everything in Seaborn using the low-level options from matplotlib. And for example, here is just a box plot, right? We're just doing the age group versus the theory of mind measure still, and we plot it there. But then what you want to see is that stuff can change. So if we change our palettes to greens _D, then the whole thing has changed to have slightly greenish hues. So just have a good look at the different arguments you can play around with. Here's a link that tells you all about the different palette choices you can choose and color choices. Another interesting thing is that in Seaborn you can very easily sort of change the style of your plot by setting the style or the context arguments with the set style function. So here we have a set style as white grid, and you can see that there is indeed a white grid behind it. And there's also, you can set the context to a notebook context. And you can see that this changes it ever so slightly. It's slightly bigger and easier to see if you're inside a notebook like this Jupyter notebook. And the plots are extremely customizable, and you can go down in level, say from Seaborn to more matplotlib sort of functionality. So in this case, we're setting style, setting context, we're creating our box plot, but now we're using some stuff from lower down from matplotlib to change how these Seaborn plots look. So in this case, I'm modifying the x-axis, we're adding ticks to the x-axis, and we're also changing the y-axis, we're setting a title to the graph, we're adding a little text to it, we're adding significance bars, and all this sort of stuff, really. And you can just do it very easily. You just need to go through the documentation and really search for what you want to do. Setting an X label is as simple as calling the setX label function. And as you can see, we've done all of those changes here. And that's pretty much it. That's it for the lecture today. I hope you've enjoyed it. I hope you've found it useful, and it will serve you well when you are creating some plots and you're not entirely lost as to what to do when you need to visualize data for exploration purposes or for creating pretty figures for communicating your findings. There's some recommended readings. If you go to the notebook, you will find that there is this link that teaches you about multi-dimensional plotting with Seaborn. This is a great resource. I already mentioned it in the slides, but this is a great resource for finding code for all sorts of different plots that it's very good to find inspiration from. And then here is a link that has a few more don'ts of plotting as opposed to things you should do. And I think that really is about it for today. So I hope you've learned quite a bit and enjoyed this. Plotting is a really cool thing, and yeah, have a good time with it.